Okay, so it's a sequence in which the ratio between any two terms is constant. So when you divide one term by the previous term, you get the same result every time. Now, we may need to do that a little bit more than we did with the arithmetic. Arithmetic, it's a little bit more obvious when you're adding and subtracting, multiplying, dividing sometimes can be a little fuzzy. So let's look at these examples. Let's determine whether we're talking about a geometric sequence or not. If we are, then we'll identify the common ratio and then give the next three terms. First example, 6, 12, 24, 48. We're multiplying by the same thing every time? Absolutely. We're multiplying by 2, so the common ratio here is 2. 6 times 2 is 12, 12 times 2 is 24, 24 times 2 is 48. If we continue that pattern, we get, what, 96, and I'm not trusting myself today, 192, and 384. All right, number 2, we have 810, 270, 90, 30. I think it becomes a little bit more obvious with terms 2, 3, and 4, but it would appear that we are dividing by 3, but do recall that division is the same as multiplying by a fraction. So I'm just checking it. I'm taking this term and dividing it by the previous term, and that does give me 1/3. If I do the next one, 270 divided by, 90 divided by 270, that gives me 1/3. 30 divided by 90 would give me 1/3. So our common ratio here is 1/3. So when we divide by 3, we get 10. Divide that by 3, we get 10 over 3. Here's where multiplying by 1/3 comes in handy. When you multiply fractions, remember you go straight across the top, straight across the bottom. So 10/3 times 1/3 is 10 over 9. All right, common ratios, just like the common difference, can be negative. Okay, they can be negative. When we look at number 3, we've got -2 to +10, +10 to -50, -50 to 250. We are multiplying by -5 every time. So the common ratio, it can be a whole number, it can be a fraction, it can be positive, it can be negative. So when we multiply that by 5, we get what, -1,000 something, 1250 times -5, 6250, and -31,250. So arithmetic sequences, they do over time get bigger. The terms definitely get bigger, or more negative, either way, whichever way we're going. But geometric sequences obviously have the potential to get much bigger, much faster, because we're multiplying by a constant as opposed to just adding or subtracting that constant. All right, number 4, let's see here. We multiply by 2. We don't multiply 8 by 2 to get 20, so this is not a geometric sequence. Number 5 is another example of where we have a negative, because you're alternating positive and negative terms. So I know that if it is geometric, it is a negative common ratio. It would appear that it is -1/4. 4 times -1/4 is -1. -1 times -1/4 is +1/4. Multiply that by -1/4, we get -1/16. So that puts us, what, next term would be +164. Kind of going through the powers of 4. And then -1 over 256. And then +1 over 256 times 4 is 1,024. Okay? Let's just look at one more. Let's look at number 8. I think pretty obvious what's going on here, but number 8's a little bit weird because we start with this decimal and we get 8, we get 20, we get 50. So let's just see. It's not very obvious what we multiply by, so the easiest way to do it is just to take a term and divide it by the previous term. So 2.5, let's see if the same is true for the next 2. Yep, And then 50 divided by 20 is also 2.5. Okay, so the common ratio, let's express that in fraction form though. Let's write that as 5/2 since it is the ratio. A ratio is a fraction. That also makes it easier to compute. The next term would be 125, right? Because 50 divided by 2 is 25. 25 times 5 is 125. I am going to use my calculator now. Because it does give me a decimal. I usually prefer things in fraction form, but since the original sequence had a decimal, I'm just going to roll with it. If the original sequence had fractions, I would keep it in fraction form. All right, so just like with arithmetic sequences, we have a nice neat formula to figure things out. The same thing is true about geometric sequences. We can find the nth term of any geometric sequence using this formula. It starts out similar to the arithmetic. It's your first term, but we're not adding because we're multiplying. So it's the first term times the common ratio raised to the n minus 1 power. It's the common ratio raised to the n minus 1 power. Where a sub 1 is, of course, your first term, and r is still, of course, the common ratio. N is whatever term we're dealing with. Now, let's think for a second. I kind of mentioned this before. The geometric sequences have the potential to get very big very quickly. Well, it kind of makes sense. If we look at what type of function this is, n is our variable. It's in the exponent. This is an exponential function. Exponential functions grow faster than any of the other functions that we've been dealing with. If we go back to our arithmetic formula, that was a linear function, right? N is our variable. That's a linear function. So exponential definitely grows a lot faster than a linear function does. I just wanted to bring that out. Okay, so this says write a rule for each sequence and then find a sub 6. Find the sixth term. So a sub n is equal to the first term in this sequence. It is 1 times the common ratio. Well, we're multiplying by 5 raised to the n minus 1. Now, here's the deal with geometric sequences. Usually, there's not really any simplifying that we can do. Now, in this case, I am going to rewrite it just a little bit just because multiplying by 1 doesn't do anything, right? Multiplying by 1 just gives you whatever it is back. So you really don't need that 1 times 5 to the n minus 1. But if this were something other than 1, just a little reminder, go back to those exponential rules. You are not allowed to multiply by that base. Okay? You're not allowed to combine bases unless they are the exact same base, and they're not. Okay? So that's our formula. Let's find the sixth term by simply plugging in 6 into our equation. So that's 5 to the 5th, which is 3,125. So again, gets big really, really fast. When your common ratio is greater than 1, that sequence is going to produce large terms very, very quickly. Let's look at number 10. 130, 65, 32.5, 16.25. What does it look like is happening? Dividing by 2, multiplying by a half. It's fine if you need to check it. Okay, divide some of those terms by their previous terms and you can confirm that. So let's write the equation. A sub n is equal to the first term times our common ratio is 1/2. It's just convention that you always put parentheses. When your base of an exponential is a fraction, put parentheses around it. Okay, that's what we did before. I just want to keep that going. All right, so that's our equation. Let's find the sixth term. Okay, 130. Again, there's no simplifying that we can do this one. You cannot multiply the 130 by the 1/2. You're not allowed to do that because the 1/2 has an exponent. So you just have to leave it. Now, be careful when you put this in your calculator. For me personally, subtracting 1 is not a big deal. So I'm just going to go ahead and do that part. Put the 1/2 in parentheses and raise it. I'm just going to raise it to the 5th. Because if you don't do that part in your head or by hand or however you want to look at it, then if you just do this, what your calculator is going to do is it's going to follow order of operations. It's going to raise 1/2 to the 6th power, it's going to multiply by 130, and then it's going to subtract 1. Adding and subtracting comes last. So if you're not going to subtract it yourself, you have to put it in parentheses. When there's more than one number in your exponent, you have to put it in parentheses. Okay, if I hadn't have had those parentheses right there, I would not have gotten the correct answer. So that's 4.0625 is our 6th term. Okay, so just be careful with things like that. It's simple, you just have to look out for the details. All right, let's look at number 14. And number 14. Negative 3,200, 800, negative 250. So what's our common ratio looking like here? Negative 1/4. So a sub n is equal to our first term, negative 3,200, times parentheses, negative 1/4, raised to the n minus 1. Again, no simplifying can be done the way that that is. We technically can simplify it, and I'll show you that here in a second. Plug in 6 to find the 6th term. Negative 3,200 times negative 1/4 raised to the, again, just do it by hand, positive 3.125. Now, when you are writing the equation for me, I'm fine with you leaving it exactly like this, but I want to show you it is possible to manipulate this a little bit, and I just want to show you in case I have seen questions that like ask which of the following could be the formula, and they have it written in different forms. So it can be manipulated. You just have to be careful with that manipulation. So here's what I'm going to do. I'm going to use my rules of exponents to break apart that exponent right there. It's n minus 1. Well, what's the rule? When we multiply like bases, what do we do with the exponents? We add them together. So I'm going to break this apart. Okay, if I'm at this point right here that I just wrote down, and I'm trying to go right here, they have the same base, so I add their exponents. So that is equivalent right there. Okay, that is equivalent. Now, raising something to the negative exponent flips it over. Okay, raising something to the negative exponent flips it over. Now, you can certainly do this part in your calculator, but we should talk about it anyways. So negative 1/4 to the negative 1 is actually negative 4. Negative 1/4 to the negative 1 power is actually negative 1. It doesn't get rid of the negative. It just flips it over. And then we can multiply the negative 3,200 times the negative 4. So another version, excuse me, of this explicit formula, these are equivalent to one another right here, okay? These are equivalent to one another, and let me prove it. Let me get the 6th term from this version of the explicit formula. So that constant times negative 1/4 raised to, this time it's just to the n, so if I'm trying to find the 6th term, I raise that to the 6th. I got the exact same value. Okay, so all I did was use my properties of exponents to go backwards. If I'm adding or subtracting something right here, I can break it up. Because my properties of exponents say if I'm multiplying by bases, I add the exponents together. So I'm just going backwards. I can simplify this, and then because now it no longer has an exponent, I I can combine it, I can multiply it by that constant. So, okay. You all want me to do another one like that so you see it again? I think so. Y'all don't want to, but we want to. All right, let's look back at number 12. Okay, let's look back at number 12. We're multiplying by 3 every time there, so its equation is 8 times the common ratio is 3 to the n minus 1. So I can break this apart. I can write that as 3 to the n times 3 to the negative 1. The negative exponent flips it over. So 3 to the negative 1 is the same as 1/3. Now I can multiply the 8 times the 1/3. This is exactly the same thing as that. It's just written in different terms. Okay, again, I can prove it by finding the 6th term using each formula. So this is the original one, and then this would be the other version of it. They give me the exact same term when I plug in 6 for n in both of them. Okay, so a sub 6 is 1,944. Questions about that manipulation? Okay. Again, I'm not going to require you to do it. I don't think the answer key has it written that way, but I did want to show you so that if it's asking which one works, both of them work. Okay, both of them work. Don't think that the other one doesn't work just because it looks different. You can manipulate that. All right, so let's look at example number 16. Let's look at number 16. It says use the information given to find the indicated value. They give us a sub 5 is negative 68 and r is negative 0.5. We want to find a sub 1. Okay, we want to find a sub 1. So what I'm going to do is I'm going to write my general formula here just to remind myself. That's my general formula for any geometric sequence. And I'm going to plug in some stuff that I know. They gave me a sub 5 as negative 68. So I'm going to consider 5 to be my n. So a sub 5 is negative 68. A sub 1 is what I'm looking for. They give me the common ratio, negative 0.5. And like I said, n in this case is 5. So if I'm solving this for a sub 1, I'm going to divide by that term right there, right? Because it's a sub 1 times that term. So if I need a sub 1 by itself, I'm going to divide. So let's find that, negative 0.5, whoops, parentheses. Always put parentheses, especially if it's a negative, if you're raising it to a power. I got away with it right here because it was a positive number. But if it's a negative number, you have to put parentheses around it. So negative 0.5 to the 4th, and we're going to divide negative 68 by that number, and that is our a sub 1. Okay, that is your a sub 1. Let's look at number 18. Similar kind of idea, but this time they give us different information. This time they tell us the 2nd term, and they tell us the 5th term, and they want us to find the 4th term. They tell us the 2nd, the 5th, they want us to find the 4th. So we're probably going to need the common ratio. This is like what we did yesterday with the arithmetic. We have, and just since this is a pretty simple example, I'm going to kind of write it out here. My 2nd term is 6. I don't know my 3rd. I don't know my 4th. I know my 5th. 0.048. So if every time I multiply by the common ratio, how many times have I multiplied by the common ratio to get from 6 to 5? Or excuse me, from 6 to 0.048. 3 times. So I started with 6. And I multiplied by the common ratio 3 times. If I multiply by the common ratio 3 times, r times r times r is not 3r. R times r times r is R cubed. And that's what gives me that term right there. So if I'm solving for my common ratio, I'm going to divide by 6. What's the last step to get R by itself? Cube root. Okay, R is being cubed, so the opposite of that is the cube root. So math number 4 is our cube root, 0.008. R is 0.2. R is 0.2. I want a sub 4, so I start with 6. I multiply by the common ratio once, and then again, and that will give me a sub 4. 6 times 0.2 is 1.2 times 0.2, 0.24 times 0.2, 0.048. I just wanted to confirm that I was getting to the right place. Okay? Any questions about that? All right, let's look at this application real quick. Jackson bought a brand new car for $38,000. If the car depreciates in value by 20% each year, what will the car be worth in 8 years? So this is a geometric sequence because it's depreciating by a certain percentage every year. So our formula, A sub n is equal to our first term. Well, our first term would be the initial amount times our common ratio. Now be careful with this. Okay, it depreciates in value by 20%. But this equation is representing how much it's worth. So if it depreciates by 20%, what percent of its original value is still left? 80%. Okay, so the common ratio here is actually the 0.8 because this is representing how much the car is worth. The 20% is how much it's losing. The 80% is how much it's keeping. Okay, to the n minus 1. So if we want to know after 8 years, then we're plugging in 8 into this formula. So that's being raised to the 7th power. After 8 years, it is only worth $7,969, and we'll be generous and round that up to 18 cents. Okay, so 20% depreciation. I don't know whether you think that sounds like a lot of depreciation or not a lot of depreciation, but it's probably pretty average. Honestly, it's probably pretty average. We're talking about a $38,000 car. It's not going to be worth much after 8 years. And so think about that in the future when you decide to purchase a vehicle. Sometimes it's better to go with used. All right, let's go ahead and talk about the series really quickly, and then we'll do the practice for everything.